So consider the two set of images below, where the left is the original image signal and the right one is an image corrupted with an additive uniform noise. So as we have seen, the additive uniform noise looks something like this, where F is the original image channel, where F is the original image signal, and epsilon is a small noise with a uniform distribution, and our I of x, y is the resultant image. So this is our original image signal, and this is our final corrupted image. So this is corrupted with a uniform noise, with a noise having a uniform distribution between negative 0.1 and 0.1. So we obtained this image by normalizing the pixels of this image. So we converted all the pixels in this image in the range 0 and 1, and then we added a uniform noise between negative 1 and 1 to obtain this final image. And we corrupted 60% of the pixels of this image, where the pixels were selected again uniformly from all the pixels in the image. Likewise, in this image we corrupted 75% of the pixels, again uniformly selected, and the noise had a uniform distribution between negative 0.2 to 0.2. So this is what an image corrupted with a uniform noise looks like. Now we will discuss, for the mathematical completeness, we will discuss some of the properties of a uniform distribution, mainly the mean, the two parameters, the mean and the variance of a uniform distribution. So assume that we have a random variable z with uniform distribution between a and b. So in that case, the mean of the variable z, which is computed as integral a to b z into pz, where pz is the probability density function of z. The expected value of z following the distribution p of z is this. So the expected value of z is simply a plus b over 2. We can see this by performing this integration. So we have p of z is constant in a and b, so we can just simply write it as 1 over b minus a. Then we have integral a to b z dz, which is simply 1 over b minus a z square by 2 from a to b, which is simply 1 over twice of b minus a into b square minus a square, which is a plus b over 2. So the mean or the expected value of a random variable z with a uniform distribution between a and b is simply a plus b over 2, and the variance of this random variable z with a uniform distribution is b minus a whole square over 12. And we can again compute this variance So the variance of a random variable z So the variance of any random variable z written as var of z is given by the expected value of z square minus the square of the expected value of z. So we have seen that the expected value of z is simply following a uniform distribution is a plus b over 2. So we just need to compute this term, expected value of z square, and again we can compute this as expected value of z following a particular distribution p of z simply integral a to b z square pz dz, which equals to 1 over b minus a integral a to b z square dz, which is simply 1 over b minus a z cube from a to b, which is equal to b cube minus a cube over thrice of b minus a. We can expand the numerator further. So after expanding the numerator, we get b minus a into a square plus ab plus b square over thrice of b minus a. So this denominator cancels out with this term in the numerator, and this function is defined only when b minus a is not equal to 0. So putting everything together now, the variance of z is expected value of z square minus expected value of z squared. So putting everything together, we get variance of z is a square plus ab plus b square over 3 minus a plus b square over 4. We can again do the math and we just do it for the sake of completeness. So a square plus ab plus b square times 4 minus a square plus b square plus 2ab times 3 over 12, which gives us variance of z is equal to a square plus b square minus twice of a into b over 12, which is equal to b minus a whole square over 12. So to summarize, if we have a random variable z with a uniform distribution between a and b, then its expected value is a plus b over 2, and its variance is b minus a squared over 12. So that covers our discussion of the uniform noise model in an image.